We will now take 30 minutes to explore several grand and profound cosmological questions. I hope you can settle in and patiently see it through to the end. First question, where did the Big Bang originate? And where is the center of the universe? Second question, why is the universe 13.8 billion years old? And how was this number determined? Third question, why might the element lithium upend the Big Bang model? Fourth question, what is dark flow? And what is its impact on theories of the universe's origin? For us tiny humans, the universe is a wondrous and incomprehensible place. Our short lives are but a fleeting moment, like a shooting star in the long history of the cosmos. And the things we consider constant, like space and time, operate by laws that are often vastly different from our initial expectations. So, as you watch the following content, try to set aside your preconceived notions and let your mind expand freely like the stars. To answer the question, where is the center of the universe? We first need to understand the Big Bang theory. Simply put, about 13.8 billion years ago, all the matter in the universe was compressed into a singularity of extremely small volume and extremely high temperature. At that time, not even atoms had formed. There was only a dense soup of fundamental particles. From that moment, the universe began to expand rapidly, then slowly cooled, giving birth to atoms, stars, and galaxies. Now, the expansion of the universe, combined with the principle of the constant speed of light, turns the cosmos into a time machine. When we observe galaxies in the universe, we are not seeing them as they are now, but rather the light they emitted long ago. Relatively nearby galaxies appear more mature because they have evolved over billions or even tens of billions of years. Meanwhile, more distant galaxies look younger because their light has taken a very long time to reach us. So, we are seeing them as they were shortly after the universe's birth. In reality, these galaxies are as old as our own Milky Way, and due to cosmic expansion, they are no longer in the positions we observe them in today. The expansion of the universe is not an explosion from a specific point outward, but a uniform, proportional expansion of space itself. This means the universe has no definitive center, or rather, every place in the universe is the center. Because no matter where you are, everything around you is expanding away in the same manner. However, this expansion isn't perfectly uniform. On smaller scales, gravity still dominates, pulling matter together into galaxies and galaxy clusters, eventually forming the large-scale cosmic web structure. As the universe continues to expand, the voids between these web-like structures are stretched ever larger. Astronomers use the Hubble constant to describe the expansion rate of the universe. The current measured value is approximately 73.2 kilometers per second per megaparsec. This means that a region of space about 1 million light-years across expands at a rate of 80,000 kilometers per hour. The speed is cumulative from the observer's point of view. For example, from Earth, the farther a galaxy is, the faster it recedes from us. A galaxy 46 billion light-years away would be receding from us faster than the speed of light. We call the spherical volume with a radius of 46 billion light-years the observable universe. Light from celestial bodies outside this sphere will never be able to reach Earth. This also means we cannot know anything about what lies beyond the observable universe. This is why we don't know if the universe is finite or infinite. Even if the universe is finite, it cannot have a boundary in the traditional sense. It would likely be a finite, unbounded, cyclical structure. Because what we call the universe inherently includes everything. If the universe had a boundary, what would be beyond it? If we want to know where the Big Bang originated, where in the sky should astronomers look for its starting point? The answer is everywhere. Because from its birth, the universe has contained everything. Only its size has changed, from very small to its current vastness. The Big Bang did not happen at a specific coordinate, but was the expansion of all of space itself. This image is the so-called cosmic microwave background, CMB. It is a snapshot of the universe shortly after the Big Bang. Using space telescopes that detect microwaves, it can be observed in every direction in the cosmos. About 380,000 years after the Big Bang, the universe was still very hot, around 2,700 degrees Celsius. Although this heat would have emitted visible light, we cannot see it as such. The expansion of the universe has stretched the wavelengths of this electromagnetic radiation by a factor of 1,000. This means the photons no longer reach Earth as visible light, but as microwaves. So, by observing these microwaves, we can understand what the universe was like before galaxies formed. This makes this image the oldest picture of the universe we can possibly see. The tiny variations in the image are the seeds that later formed the cosmic web structure. We are fortunate because, aside from the CMB, there are almost no other bright microwave sources in the universe, which means this image is not contaminated by other radiation and shows a complete picture of the universe 380,000 years after the Big Bang. So, can we see an even earlier universe? The answer is no. Before that time, the universe was in the epoch of photon decoupling. Newly formed atoms interacted with a dense plasma of fundamental particles, preventing photons from traveling freely. In summary, the universe has no absolute center, or rather, its center is everywhere. When we use microwave telescopes to observe any corner of the cosmos, we are actually peering into the face of the universe shortly after the Big Bang. As mentioned before, this characteristic truly showcases the wondrous nature of the universe. Next, we explore the question, why is the universe 13.8 billion years old, and how was this number obtained? We currently see the universe expanding and cooling. Aside from gravity pulling matter together, everything in the universe is moving away from everything else. The speed of this expansion is known as the Hubble constant. An obvious conclusion from an expanding universe is that matter is being diluted. The space between things is getting larger. The expansion of the universe also has a less obvious consequence. The wavelength of light is stretched. This phenomenon is called redshift. High-energy, high-frequency waves emitted shortly after the Big Bang eventually became lower-energy microwaves, the cosmic microwave background. This is also why the James Webb Space Telescope uses infrared wavelengths to probe space. The photons from galaxies billions of light-years away have been redshifted so much that we need infrared telescopes to observe them. Photons contain energy. Higher-frequency waves carry more energy, meaning they are hotter, while lower-frequency waves are cooler. Therefore, we say the universe was once dense and hot, but now it is larger and colder. But how does knowing this help us calculate the age of the universe? First, we need to make some assumptions about the cosmos. First, on a large scale, the universe is homogeneous and isotropic. Although the universe contains superclusters dense with galaxies, as well as supervoids with almost nothing, we assume that across the vast expanse of the entire universe, it is roughly uniform. Second, we assume that the laws and properties of the universe are the same in all directions. Third, we assume the Big Bang happened everywhere at the same time. Under the laws of general relativity, if these three assumptions hold true, then there is a connection between the age of the universe and the way it has expanded throughout its history. With these assumptions, we can measure the distances and brightness of objects like stars, supernovae, and galaxies. For example, Type I supernovae have a very consistent absolute brightness when they explode, making them ideal standard candles for measuring cosmic distances. Simply put, since the brightness of a Type I supernova is known, we can calculate its distance by observing how dim it appears, which in turn tells us how long ago we are seeing it. We can also look for fluctuations in the cosmic microwave background, which is a snapshot of the early universe, and compare it to the galaxy clusters we see today to understand how the universe has evolved and expanded. Based on the universe's expansion from the past to the present, scientists have calculated the composition of matter in the observable universe to be roughly 68% dark energy, 27% dark matter, and 5% visible matter. So what are dark matter and dark energy? We don't really know yet. However, we can observe the effects they produce. Dark energy is thought to be the driving force behind the universe's accelerated expansion, because without it, the expansion should have slowed down by now. Dark matter is a type of matter we cannot see, but can indirectly prove its existence through its gravitational effects. It provides much more gravity in galaxies and galaxy clusters than visible matter does, and is also the primary force holding the large-scale cosmic web together. In fact, we can even map its mass distribution. Although we don't know what it is, we can use the effects it produces to calculate the age of the universe. We now know the universe's current expansion rate, the principle of redshift, the composition and properties of the universe, and we can observe the evolution of galaxies over time and probe the features of the CMB. By combining all this known information and using scientific theories for deduction, we can trace back to the earliest stages of the Big Bang. Using 3 different instruments to observe different aspects of the universe ultimately yielded roughly the same result. The universe is 13.8 billion years old, with an estimated accuracy of 99%. However, scientists still have some questions about this conclusion. For now, it is an approximation. As technology continues to advance, this number could be revised at any time. For instance, the upcoming Nancy Grace Roman Space Telescope and the already revolutionary James Webb Space Telescope both have special missions to help us peer into the universe's more distant past. Despite years of research in this field, we are still in the early stages of exploration. Honestly, the achievements humanity has made in understanding the cosmos are already astonishing. Who could have imagined a few hundred years ago that we would be able to calculate the age of the universe? Although every new discovery often brings more questions, isn't the relentless pursuit of truth the very essence of science's charm? In scientific exploration, few questions are more important than the origin of everything. What did the universe look like at its birth, and why did it happen? Although we are still a long way from completely solving this mystery, scientists have accumulated a vast amount of evidence to construct the basic framework of the Big Bang Theory. By analyzing the spectral data left as starlight passes through matter, we are, like patient puzzle masters, gradually piecing together the outline of the Big Bang Theory and trying to depict the cataclysmic creation scene of the early universe. However, the path of scientific exploration is never smooth. It's like trying to complete a giant jigsaw puzzle and encountering a piece that just won't fit, no matter how you try. It's frustrating and confusing, making you realize something is wrong, but you can't immediately pinpoint the problem. Today, the Big Bang Theory faces such a dilemma. Have we misunderstood the correct orientation of the puzzle, or have we overlooked a crucial piece? The core of this mystery points to an element we see everywhere in our daily lives: lithium. This element, vital in medicine, alloys, and especially in mobile phone batteries, is unusually scarce in the cosmos, with its observed amount far from theoretical predictions. This has posed a challenging question to scientists. Where did all the lithium in the universe go? This puzzle, which has baffled the scientific community for years, remains unsolved. To truly answer the ultimate question of where we come from, we may have to re-examine our current cosmological model. To delve deeper into this issue, let's start with the basic properties of lithium. As a member of the alkali metal family, lithium has a relatively simple structure but is exceptionally soft, so much so that it can be easily cut with a standard steel knife. Many have witnessed its curious reaction with water in school chemistry classes, where it reacts vigorously to produce lithium hydroxide and hydrogen gas. In modern technology, lithium is widely used. Thanks to its high electrochemical potential, it has become a core material for batteries in devices like mobile phones and laptops. But for cosmology, lithium's most crucial feature is its internal structure. Its nucleus contains only 3 protons, meaning it is one of the few elements that could form in the early universe. Because of this, the theoretically predicted amount of lithium in the early universe has become a key test of the Big Bang model's validity. So, how do scientists envision the early evolution of the universe? And why does the lithium anomaly challenge the current theory? In truth, the origin of the universe is still shrouded in thick fog. In the 1920s, humanity discovered that the universe is expanding. This led Belgian cosmologist Georges Lemaitre to propose a bold hypothesis. Since the universe is getting larger and colder, looking back in time, it must have gone through a smaller, hotter phase. Following this logic, at the dawn of the universe, all energy was concentrated in a single point, called a singularity, with near-infinite temperature and density. This idea became known as the Big Bang model. However, the concept of infinity poses a great challenge to theoretical research. Although Einstein's theory of relativity can accurately predict the motion of objects in a gravitational field, once infinity is introduced into the field equations, all calculations become inaccurate. We still lack a perfect set of equations to clearly describe what happened at the very moment of the universe's birth or what force drove its expansion. Even more problematic, the extreme conditions of the singularity erased any information from before it, as if it were thrown into the universe's hottest furnace and vanished without a trace. The only thing we can be certain of is that the universe was born in some way, but the specific process remains an unsolved mystery. At the instant of the universe's birth, lithium did not exist. The temperature was unimaginably high, but just 1 second later, as the universe began to expand, its temperature dropped to 10 billion degrees Celsius, 1,000 times the temperature of the sun's core. At such high temperatures, matter could not form stable states. The fundamental forces that hold atomic nuclei together were insignificant against the surging tide of energy. The entire universe was like an ocean of radiation. Fortunately, relics of this period remain today in the form of the cosmic microwave background, which has become a key piece of evidence for scientists to verify cosmological models. The universe did not remain in a state of pure radiation for long. Just 99 seconds later, its temperature cooled to 1 billion degrees Celsius. At this point, the strong nuclear force began to take effect. The first protons in the universe started to form and combine with neutrons, creating hydrogen atoms and the hydrogen isotope deuterium, composed of 1 proton and 1 neutron. Hydrogen and its isotopes, as the most common elements in the universe, dominated this wave of element creation. But hydrogen was not the only element. The universe was still filled with extremely high energy, and hydrogen protons frequently collided and fused, quickly forming the larger and more complex element helium, which contains 2 protons. Calculations show that in the primordial universe, matter was composed of about 76% hydrogen and nearly 24% helium by mass. Sometimes, in very rare cases, a proton would combine with 2 others to form an isotope of lithium, bringing the proton count in these atoms to 3. By mass, lithium accounted for only 0.0000007% of the matter in the early universe. However, it is this minuscule amount of lithium that has become a major puzzle for the scientific community. By analyzing stellar spectral data and studying how light changes as it passes through clouds of matter, scientists can understand the distribution of elements in today's universe. Overall, observations align well with theoretical predictions. Take our Sun, for example. By mass, it is 71% hydrogen, 27% helium, and the remaining 2% is other heavy elements. This is reasonable because, during its evolution, the Sun has had enough time for more nuclear fusion, slightly altering the proportions of these elements. The elemental ratios elsewhere in the universe are similar, providing strong evidence for the correctness of the hot Big Bang model and our calculations, indicating that the universe did indeed evolve in this way. But our prediction for lithium is off. Although the predicted amount of lithium in the early universe was extremely low, this prediction is actually 3 times higher than the observed results. In other words, when we study the spectra of primordial stars, the farther away the star, the longer its light takes to reach us. The amount of lithium we observe is far lower than expected. And the lithium mystery doesn't end there. In the early universe, the lithium isotope we observe is mainly lithium-7, with a nucleus containing 3 protons and 4 neutrons. There is also another isotope, lithium-6, which has 1 less neutron than lithium-7, making it less stable and abundant. Theoretically, for every 100,000 lithium nuclei, only 2 should be lithium-6. However, while the total amount of lithium in the universe is lower than expected, the ratio of lithium-6 to lithium-7 is too high. In the early universe, the abundance of lithium-6 is 1,000 times higher than predicted. So, what does this finding mean for the hot Big Bang model? As the most widely accepted theory of the universe's origin, does it really need to be completely overturned and rebuilt? Not necessarily. There are 2 possible paths forward. One is to revise and improve the existing Big Bang theory. The other is to find a completely new explanation that can answer the current questions. In scientific exploration, when faced with such contradictions, there are usually only 2 possibilities. Either the observational data is flawed, or the theoretical model itself is deficient. The hot Big Bang model has been studied for many years, and its status cannot be easily shaken. To date, no other theory can explain the existence of the cosmic microwave background and the abundance of hydrogen and helium in the universe as precisely as it does. The actual observed values of these elements almost perfectly match the predictions of the hot Big Bang model. Such a high degree of consistency is no coincidence. However, as research deepens, scientists' doubts about the model are also gradually increasing. Take the famous physicist Stephen Hawking, for example. He was once a major proponent of the idea that the universe originated from a singularity, but later changed his mind. In A Brief History of Time, Hawking mentioned, "The results of my research with Roger Penrose were widely accepted, and at the time, almost everyone believed that the universe began with a Big Bang singularity. Ironically, I have now changed my mind, and am trying to convince other physicists that the universe did not actually have a beginning singularity. Because once quantum effects are taken into account, the singularity may cease to exist. However, quantum effects involve complex theories and calculations that are difficult to detail in this video. Besides, even if the singularity disappeared due to quantum effects, it wouldn't necessarily solve the critical problem of lithium abundance. This phenomenon precisely shows that the study of the universe's origin is still a constantly evolving frontier in physics and cosmology. Currently, there is no complete and flawless theoretical system. Perhaps in the future, scientists will be able to optimize the existing model, making adjustments while retaining the core framework to perfectly solve the lithium abundance problem, making theoretical predictions fully consistent with actual observations. Besides the possibility of a flawed theoretical model, there is another possibility. Our observations are biased. And this speculation is not without basis. The abundance of lithium in the universe is extremely low. When we try to trace back to the early universe, accurately determining the lithium content in the interstellar medium becomes exceptionally difficult. Currently, scientists mainly use spectral analysis to detect the composition of the interstellar medium. The principle is to emit light towards a target and then observe which spectral lines are absorbed with a spectrometer to determine the elemental composition of a specific nebula or dust cloud. But as the distance to the observation target increases, the difficulty of this technique rises exponentially, eventually making it almost impossible to obtain accurate results. Therefore, scientists have to settle for the next best thing, observing the spectra of primordial stars to infer the lithium situation in the early universe. However, stars are extremely special celestial bodies. The complex nuclear reaction processes inside them alter the lithium content, not only potentially converting lithium into other elements, but also possibly changing the abundance of lithium-6. Although we do not yet know the specific mechanisms of these reactions, we can be certain that primordial stars do not fully represent the true state of the entire universe at that time. Perhaps with a breakthrough in observation technology, we will be able to more accurately measure the total amount of lithium in the early universe. Then, the problem of the discrepancy between lithium abundance and theoretical predictions might be resolved. Although the mysteries of the universe are profound, it is amazing that with the help of telescopes and scientific reasoning, we can gradually unveil the cosmos from billions of years ago, even before matter was fully formed. The birth of the universe was not a chaotic accident, but followed some underlying order. It is this order that guides scientists to constantly explore, unlock the principles of the universe's operation, and solve the deep mysteries hidden within. Although we are still fumbling in the dark, I firmly believe that one day, the lithium mystery and other problems perplexing the academic world will be solved. On the path to seeking the ultimate origin of the universe, every question is crucial and deserves our full effort. I eagerly await the moment when the magnificent scroll depicting the complete picture of the universe's origin slowly unfolds. In ancient times, human tribes often sat around a flickering campfire, speculating about the unknown secrets that might be hidden in the darkness of the universe. In a sense, this human desire to explore has never changed. Today, our campfire has become much more powerful. With advanced instruments like the James Webb Space Telescope, our vision has already crossed the globe and even extended to the edge of the observable universe. However, the boundary of the universe is like an insurmountable barrier. The space there is accelerating away from us at a speed faster than light, making it impossible for any matter, including light, to reach Earth from beyond that boundary, nor can it have any causal connection with us. In this sense, everything beyond the observable universe seems destined to remain an eternal mystery. But the charm of science lies in constantly breaking down established perceptions. In 2008, an analysis of hundreds of galaxy clusters revealed a startling phenomenon. These clusters were drifting towards a certain region at the edge of the observable universe at a speed far exceeding the predictions of existing theories. This anomalous motion seems to imply that beyond that ultimate darkness, some mysterious force is pulling them with a gravitational force that spans billions of light years. This phenomenon was named dark flow by scientists. So, what do we currently know about dark flow? What force is causing this phenomenon? And what kind of impact will it have on existing theories of the universe's origin? Next, we will delve into the mystery of cosmic dark flow and the disruptive challenges it may bring to theories of cosmic origin. As a controversial scientific topic, let's start with the known observational facts. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, tasked with a key mission: to map the cosmic microwave background, CMB. This faint electromagnetic radiation, originating from the Big Bang, is like the first light of the universe's birth, silently pervading all of space and becoming the core clue for decoding the characteristics of the early universe. In 2010, with the final release of the full WMAP data, this high-precision CMB map quickly revolutionized cosmology, helping scientists accurately determine fundamental parameters such as the geometric flatness of the universe, the proportions of dark matter and dark energy, and the abundance of ordinary matter. At that time, scientist Alexander Kashlinsky of NASA's Goddard Space Flight Center keenly recognized the potential value of this data. He led a research team to try to cross-analyze the CMB map with the motion trajectories of galaxy clusters, searching for possible dynamic patterns hidden in the large-scale structure of the universe. This research relied on a very subtle observation technique, the kinematic Sunyaev-Zeldovich (KSZ) effect. When CMB photons pass through a high-energy galaxy cluster, a tiny energy shift occurs in the radiation spectrum, whether due to energy exchange between the cluster's hot, thermally excited gas and the cold radiation, or because the cluster's high-speed motion transfers kinetic energy. Why do the photons? This shift is usually only a few parts per million and can only be effectively captured by statistically stacking the signals from hundreds of galaxy clusters. The research team first found a sufficiently detailed CMB map, then matched it with the positions and velocity data of over 1,000 known galaxy clusters. Shockingly, their analysis revealed a massive collection of galaxy clusters spanning 2.5 billion light-years, moving collectively towards the direction of the constellations Centaurus and Hydra at a speed of 600 to 1,000 kilometers per second. Strangely, in that direction, within our observable universe, there is no gravitational source that can explain this motion. It is as if an invisible giant hand is pulling these galaxy clusters from beyond the edge of the universe. The reason this phenomenon caused such great controversy is the core question: can matter located outside the edge of the observable universe really exert a gravitational influence on us? From the perspective of classical cosmological theory, the answer seems to be no. As mentioned earlier, when the expansion of space between 2 points exceeds the speed of light, no causal connection can exist between them. Neither matter nor energy can cross this space-time chasm, and this includes gravitational interactions. However, the theory of cosmic inflation provided a possible theoretical breakthrough for this dilemma. For those unfamiliar with the concept of cosmic inflation, one must first understand a key scientific puzzle. In the 1970s, scientists discovered that the universe exhibits astonishing uniformity on a large scale. No matter how distant a region is observed, its temperature and mass distribution are highly similar. For example, the left and right edges of the universe we observe are highly similar in physical characteristics. But these two regions have never been in causal contact during the universe's 13.8 billion year history. This contradiction is known as the horizon problem. In 1980, American physicist Alan Guth proposed a groundbreaking explanation. If all matter in the early universe was once in a unified region of interaction, similar to blue and red dyes mixing thoroughly in water, this would naturally explain the uniformity. But for the initially uniform distribution of matter to evolve into the current cosmic structure, in addition to the known Big Bang expansion, a period of superluminal spacetime inflation is needed. According to the theoretical model, this inflation occurred about 10⁻36 to 10⁻32 seconds after the Big Bang. Indeed, the scale of the universe expanded exponentially by a factor of 10^26, equivalent to expanding from the size of a bacterium to the scale of the Milky Way in an instant. Although this process is difficult to visualize, it perfectly solves the horizon problem. The uniform state of thoroughly mixed matter before inflation was stretched to all corners of the present universe by superluminal expansion. Even those regions now separated by more than tens of billions of light years were once within the same interactive range before inflation. Based on inflation theory, the dark flow phenomenon gets a possible explanation. In the primordial universe before inflation, there existed a region of extremely high-density matter. Its powerful gravity pulled our region of the observable universe towards it. When cosmic inflation started, this high-density region was rapidly pushed outside the observable universe, and its gravitational effect disappeared. But due to the principle of inertia, those galaxy clusters that were initially accelerated continued to drift in their original direction, forming the large-scale flow observed today. However, this explanation faces two major controversies. First, the validity of the dark flow theory depends on a key assumption: the existence of an extremely massive gravitational source outside the observable universe. This implies that the universe might have a much denser distribution of matter than predicted by current models, which directly contradicts the core premise of Goose's inflation theory, the uniformity of the universe. According to current observations, our universe is highly uniform and isotropic on a large scale. For example, no matter which corner of the universe we observe, the density fluctuations of galaxy distribution remain within a very small range, and the overall motions of matter in the universe cancel each other out. The dark flow phenomenon challenges this understanding. It suggests that outside the observable world, the universe may suddenly cease to be uniform, and there might be huge mass sources that we cannot directly observe. This idea raises many profound cosmological questions. If the universe is indeed not uniform outside the observable range, are we by chance located in a special, flat region? What does this imply for our current theories of cosmic formation and the mechanism of inflation? More importantly, if cosmic inflation was meant to explain the uniformity of the universe, but the universe might not be uniform on a large scale, what impact would this have on fundamental cosmological theories? Another key reason for the controversy surrounding the dark flow theory is that its very existence has not been unanimously recognized by the scientific community. Although NASA's Kashlinsky team firmly believes in it, the European Space Agency's Planck team, using its more advanced detectors, obtained higher precision data on the cosmic microwave background. After a systematic analysis of 1,000 galaxy clusters, they declared that they found no evidence to support the existence of dark flow. Although the Kashlinsky team later re-examined the Planck data and insisted that a dark flow signal exists, the two sides' conclusions have not yet reached a consensus. The team has now publicly stated that it will combine WMAP and Planck data for a more in-depth analysis to provide more convincing evidence for the existence of dark flow, but the relevant research results have not yet been published. Until more conclusive evidence is obtained, the cautious scientific community is more inclined to believe that dark flow does not exist, and there is no mysterious force outside the observable universe pulling galaxies towards it. Science doesn't care which explanation is more convenient. The truth is the truth, no matter how complex or simple it is. Perhaps one day in the future, we will be able to break through our observational limits and truly uncover the mysteries beyond the observable universe and whether dark flow really exists. But even so, a new cosmic boundary will then emerge. Humanity's exploration of the unknown is endless. The wonder of the universe lies in this. There are always vaster territories of knowledge waiting for us to explore, and humanity's thirst for truth burns eternally like the ancient campfire.